So the first thing I want to show, just a quick announcement. Just because there's always like halfway through the semester, somebody finds this out for the first time and it blows their mind. I just want to show it right away so you don't have to get your minds blown at all. But these sections of the course website do collapse, and then they stay collapsed when you refresh. You did get your mind blown. You read the syllabus, you know what's in there. I basically read it to you on Monday. You can collapse that, and then you don't have to scroll through it every single time. And each section of the course collapses when we're done with homework 1 stuff. You can get homework 2 right at the top. So just to point that out, because some people don't notice it. And yes, that's a UI, UX problem, but I'll just show you all, and then I don't have to fix it. So let's talk about stuff. Oh, I thought I got rid of this. But let's talk about TCP IP. You've probably heard this tons of times. A lot of you might be fairly familiar with it, but let's talk about it. So let's dive right into content, right? I don't have any other announcements, do I? Oh yeah, just a reminder, I'll watch the lecture channel on Discord during lecture. If you see me staring at my phone, I'm not ignoring y'all. I'm just looking for questions. Trevor, Nicholas gave me a heads up. You wanted to do it in C++. You're insane. Yeah, if you want to do that to yourself, I guess you can. If you want to write the homework in C++ and then have that code called from Python, technically you're still writing it in Python. Yeah, if you want to do that to yourself. I don't recommend you do that unless you're insane. Trevor's insane, so you can do that. Are there recitations this week? So I'm still in the honeymoon phase. I'll answer questions like this, but once we get further in the semester, I'm not going to answer questions like this. But there's no recitation sections the whole semester. They're replaced by your group meetings, which start on week 5. It's in the syllabus. It is in the syllabus, right? I did add a project section, or did I add this before? No, I added that before the first day of class. But it's right here. Boom. No recitations. All right, so let's get into content. Can you do if you want to do it in Fortran and have it called from Python, go for it. But it's got to be, I have to be able to access your call through Python means. And we'll see that if you looked at homework 1, we're going to look at it. These slides won't take the whole lecture, so we're going to look at homework 1 by the end of this, and you'll see the first thing I finally get to do because I'm standardizing the language. So you do have to fit that interface. You fit that interface and end up making syscalls to some compiled code in another language. I don't know why I would stop you. You're just going to learn more if you do that, so why not? When we have slides, just something I like to do, just a logistical note I want to put out there. You'll see me do this at the beginning of each lecture. I'll download the slides from the course website like thus. I'll download it, and then sometimes it'll say, you have 8 copies of this already on your hard drive. Why are you downloading it again? Why are you doing this? I'll do that because I always want to make sure what I'm presenting is exactly what's posted on the course website, to make sure what I'm doing up here is exactly what you have access to on your machines as well. So I do that mostly as a sanity check for myself, just to make sure I didn't mess something up. Sometimes I'll download the slides, and then I'll get to a slide and be like, oh, this doesn't have my updates in it. This isn't the latest slides. And then I'll go update the website real quick, download them again in lecture, give you a quick Git tutorial as I'm doing it, and then get the latest slides if I ever mess up. But I do that just to make sure that I uploaded the right slides and that we have the latest version. All right, so let's start talking about the internet. Where else to start in web apps than the internet? Let's talk about what this is. And a lot of today's lecture is like overview stuff, background information about how the internet works, to get to some context to what we're going to be doing, where our role is in the internet at large. So let's talk about what this thing is at all. Like, what is the internet? It's this really kind of nebulous thing. It's very loosely defined or mysteriously defined. It seems to be magic, seems to just work, which will be the first theme that you're going to notice in this course is we're going to dispel magic. If there's anything mysterious about how the internet works, I want to dispel that, and you're going to find out that the internet's actually kind of boring. The way it's set up is kind of dumb, actually. Not really. There's a lot of very sophisticated solutions to problems that arose, but it's dumber than I expected it to be, at least. Maybe it's just a me thing. But let's do it. Let's talk about it. So first, local area networks. This is what we're all used to. If you have internet at your house, you buy a router, and your router is a router and an access point in one. So we call that a wireless router usually. But it's a router that routes packets through a network and also gives us Wi-Fi. So it's an access point. We have, I didn't look before lecture. I don't know if we have any here in this room. Looks like there's one right there. So we have an access point. So we're all using Wi-Fi right now. Our machines are talking to that access point and allowing us to connect to UB's network. And that access point is going to talk to routers for UB's network. And then if we need something from outside UB's network, it's going to talk to the internet at large. So the internet at large, we're going to plug into what's called an internet service provider, an ISP. If we're at our houses, we call up our ISP. They come down with wires that they have. They plug us in to either the telephone poles, or if we have our utility lines underground, they're going to plug us into their network. But the big thing is, the first magic to dispel is the ISP's network is not much different than our LAN. It's just bigger. They're bigger wires. The routers are bigger. There's higher capacity. But they have physical wires running around entire neighborhoods and entire cities and plugging them into big routers that are going to route our packets using the same technologies we use in our home, the same routing technologies, the same packet technologies, the same internet protocol, the same, we're not quite talking about TCP yet, but the same protocols that we use in our home networks. It's the same stuff, just bigger wires. That's what the ISP is, and they literally just laid wires covering entire cities, entire regions with these ISPs. The ISPs don't connect everything. The ISPs actually have tier 1 networks that they connect to, which I like to call the ISPs of the ISPs. They pay tier 1 networks to use their networks, and these are the big networks. These are the networks that are connecting across cities, across countries, across the whole world. This is, if anything were to be called the internet, the collection of tier 1 networks is the internet. These tier 1 networks have agreements with each other, peering agreements, where they don't pay each other to use each other's networks. They just use each other's networks free of charge. They all decided, hey, this tier 1 network that's covering half the country, another one that's covering another half, we need to use each other's networks if one of our customers needs to talk to one of your customers, but we're going to have so much complexity and so much tracking to bill each other, we're just going to say, you know what, let's just use each other's networks free of charge. Because they figure it'll just wash out, that all the accounting would probably be more expensive than what they're going to make by charging each other. What this results in is effectively one large networks. All the tier 1 networks combined together with these peering agreements basically forms one global network, which, like I said, if I'm pointing to anything and saying that's the internet, I'd say the collection of tier 1s with the peering agreements is the internet, or the backbone of the internet. That's what you want to plug into. If you're plugged into that, you're plugged into most of the world. And any ISP is going to plug into that collection of tier 1 networks. So the ISP is going to go to a tier 1 and say, we need to plug in, and then plug into the internet. And these tier 1 networks, guess what? Guess what's going to be a theme? Nothing special. The wires are just bigger. They just have wires, cables, not really wires, but cables that they run that go from city to city, country to country, and just have really big, massive bandwidth cables that can connect across large distances. Which should bring up the question, here's examples. Here's some examples. You might have heard of some of these companies. A lot of them, like L3 Communications, you might not have heard of. Maybe you have at this, you're in the tech sphere. You might have by this point. But they're, I think, the biggest in the United States, biggest tier one. And I'd say the majority of people probably never even heard of them. We like to hate on our ISPs, but we don't even know who's actually handling our data, who could be spying on us or anything. I'm not saying they do. I don't want to imply anything. But that they do have access to all of our internet communications. But these are some of the networks that span large distances. So this should, hopefully I'm setting up the right slide now. So this should beg the question, well, that's great for I'm going to do my slides out of order, I don't care. That should bring up the question of, those are good for the United States, but how do we connect across countries? We know that we can communicate to Europe, to Asia, Africa. We can go across continents with this stuff too. How do they do that? Well, guess what the answer is still? Big frickin' cables. They literally just make big cables, plug them in on one side of an ocean, lay them on the ocean floor, and plug them in at the other side of the ocean. That's how we communicate across continents. There's no fancy technology. There's no wireless technology specifically. It's just big frickin' cables laying on the ocean floor, and that's how we connect the world with the internet. The tier one networks laid all these cables spanning the entire globe. That's how we do it. Big frickin' cables. Same technology that you have in your home, same technology your router has. It's internet packets being sent and routed through IP-compliant routers. The cables are just bigger, the bandwidth's bigger, and of course it's all fiber. The cables have tons of fiber in them to send high-speed data across continents, across oceans. But the internet is a surprisingly, at least it was surprising to me, a surprisingly physical thing. It's cables routed across the world. From that access point, we have wireless. From my laptop, from your laptop to that access point, it's wireless. And we think of the internet as wireless. It kind of gives this illusion that there is the cloud up there that's doing all this magical stuff. No, we have wireless to that access point, and then we can follow a physical cable from that router there, that access point there, all the way to someone we're communicating to in Beijing until the last few feet they have an access point and it's wirelessly going to their router. You can follow a physical cable that entire distance, including across the ocean. It's a very physical thing, very literal, physical plugging in cables to plug in continents to each other, even across oceans. Yeah. Elon would like to would like to say that. So, of course, there's Starlink. Starlink's becoming more and more popular. So maybe I'll have to update this lecture at some point. I don't know the numbers. I can't imagine them being they'll be comparable. It's hard to get faster than cables. These things are traveling nearly the speed of light, and they have to follow the curvature of the Earth, but so do the satellites. But the satellites, we got to beam up. But Starlink's in low Earth orbit, so there's not too much distance it's got to go. And we can't get line of sight here, which they can get line of sight. So there's a lot of variables. I would expect it to be comparable amounts of ping times. And then the slide that I skipped, these networks, these physical, yep. I don't have an exact number, but they do have to be maintained. They have huge ships that will dig it up, pull it up, and then repair them. I don't have an exact answer for you though, but they are prepared to do that. Oh yeah, I missed this question, but it was on my slide. Yeah, here are some examples of tier ones. Is there a tier two? I don't think so. I think a tier two would, if there were something. It might be. I might be wrong. I'm just guessing here. I haven't heard of tier twos, but if there were something that I would call a tier two, I would say the ISPs would be a tier two. But there might be a whole hierarchy that I just don't know about. It's possible, very possible. but I know tier ones are the big networks. And I did it as LAN, ISP, tier one, but it doesn't have to go like that. Like UB's LAN, UB's network plugs right into a tier one. They don't mess around with Verizon FiOS or nothing. They're not a Verizon customer or I always forget the name of the other one, but one that changed their name, Spectrum. They're not going to mess around with that. UB is going to go right to the source, plug right into the tier ones. Is there a question? Go.
So do those cables underneath the ocean, do they have like the bandwidth to carry like an entire continent like that at once?
Yeah, they have to. It's huge bandwidth. Well, and that's presumably, again, I'm no expert in exactly the logistics of it. But that's why they have so many of them. I would assume we outgrew the bandwidth of the first ones, and instead of replacing it, they'll just add another one. I would guess. I'm speculating there. And even some private companies have their own oceanic cables. It's like Google wants more bandwidth and they don't like paying tier ones. They lay their own cables. So if they need lots of bandwidth, like to run YouTube is ridiculous, they lay their own cables. Which is why Google's in a position, I'm getting a little off track, but not really. That's why Google's in a position to have, I forgot the name of it, but Google's ISP that they started in a few cities, they were trying to expand, because they have their own network. They have a massive network that spans the globe, and they can go into cities, plug into their network, and basically be a tier one, but they don't really want to be a tier one. So they can be an ISP that plugs right into their network and give you really good bandwidth. Google, what's the name of that? What's it? Google, no, Google Fi is the wireless, the cell phone one. It was a Google Fiber, maybe? I don't know. Is there another question over here? Someone? Oh. Okay. So there's another implication here, is that these networks, they're literally just wires. They're big cables. I keep saying wires, but cables that could either be copper or fiber, laid across the entire globe. And the tier ones have peering agreements with each other, and the ISPs pay the tier ones to connect to those networks. The implication is that these massive networks need to plug into each other. And they can't just plug two cables into each other and call it good. They have these locations called internet exchanges with tons and tons of wires, and they plug these networks into each other in rooms like this. I believe it's the entire 6th floor of 60 Hudson is a giant internet exchange. Or is it? No, I think the 6th floor is the backup generators, which caused some controversy. The 6th floor, I think, is all the backup generators with tons of fuel, which, of course, caused concern. But in the end, the internet won out, so we still have an internet exchange in New York. All right, so big, yeah, and it didn't update. The only change I made to these slides is I deleted this one. So then I talked about Google's network, but I thought I deleted the slide, so I didn't pull it up. But Google has its own big network with oceanic cables because they're big enough and have enough money to do that. So that's why if you're going to YouTube, it's going to go pretty quick. You rarely have performance issues with YouTube unless it's with your ISP or something else, or your machine or your device or something, or UB's network, UB's Wi-Fi, something like that. But if you use other apps, you might not get the same performance. Part of that's because Google has such a huge investment in infrastructure that they can offer things like that. They can deliver high-performance apps. Yep. Yes, 100%. So we'll talk about it in more depth, actually way late in the semester, so I'll answer it here. That's why we use HTTPS. So we're encrypting our information. So even if somebody does tap into it, they can't see what we're saying because it's all encrypted. And somebody can tap into the wires and get into the hard line and read it. They could do that, but much easier. If they're in the same room as you, like this, we can just grab your packets out of the air, out of the Wi-Fi. I could run some software, Wireshark. I could run software right here and read your packets, what your device is talking to that access point, we can just grab that out of the air. But if it's all encrypted, who cares? The answer is you should still care, but which is why we use VPNs as well. So we can't see what you're saying if it's encrypted, but we can still see who you're talking to. So I could see that what sites you're connecting to, what IP addresses you're talking to. But if you use a VPN and you're making sure everything's encrypted, which the VPN should add an extra layer of encryption if they're a good VPN, then nobody can see what you're doing. All right, and then what plugs in on the other side? So we want to plug into these tier 1 networks so we can be plugged into the backbone of the internet and communicate to any internet activated device on the planet. But more likely, we're connecting to one of these things right here. We're connecting to a data center, which is running whatever app we want to communicate to. So large companies have many, many data centers. Like Google has tons of data centers all over the globe, to the point where they actually keep it a secret how many and where these data centers are. But these data centers, this is one that's near Lockport, like probably a 15-minute drive from here. I haven't kept tabs on it if Yahoo's still using it, but it was a Yahoo data center. They're the ones who built it. And I don't know is Yahoo still a thing? I don't.
Yeah, it's still run by Yahoo, so like 5 minutes from my house.
Okay, and Yahoo is still running this data center too? Okay, cool. So Yahoo does this, and they reference as why to build it out here is that the breeze off the lakes helps with cooling. As you can imagine, actually, as you can now imagine, there's a lot of machines running inside these buildings, so heat becomes a big issue. Cooling these things is very expensive. So the cold air coming off the lake, especially in the winter, we have a nice cold climate here, really helps with cooling this data center. This one isn't inside Yahoo's. This is a different picture. I couldn't get a picture from inside Yahoo's data center, but this is what it's going to look like. They all look very similar, just racks and racks and racks of servers, which server is a term we're going to use a lot in this class. So I want to take a little bit of time to talk about what the hell a server is, because I didn't know what a server was for a while. But these are servers, I guess. Let me explain. So when we say server, we can mean one of many different things. Often we mean like a hardware server. This is a server which is basically a computer that's designed to fit in these racks, and that's it. It's the same type of hardware that you're using in your machine, except it's specialized to run 24/7 to serve web apps and things like that. But it's the same idea. They're using DDR RAM, they're using hard drives, they're using SATA or whatever. I forgot my protocols, but they're using the same protocols, the same things. But they're using like processors that are designed for this, more cores and things like that. Same technologies though. They're just computers, but they're made to fit in these racks, and they usually get specialized hardware that's made for their purposes. And of course, they're going to get, depending on what that server is supposed to be doing, if it's a storage server, it's going to have more hard drive. If it's an endpoint where everybody's hitting that server when they access the site, it's going to have more RAM, things like that, and more CPU. But they're just computers. In this course, when we say server, we mean the software that's running on these. So you're going to use your own laptop as a server when you're building your web apps. And then if your web app grows to a ridiculous point where you need hundreds and hundreds of machines running your app, then you would get a server room like this and fill it with servers. So there's the physical, the hardware server, which is what I would call these. I would say those are servers. That's pretty standardized. But then there's the software server, which can run on any machine at all. Yeah.
So would a single application be running on like one particular server?
So when you get to that size, you have it as a distributed system. Like YouTube, the app, is going to run across multiple data centers, not just multiple devices, but multiple entire data centers to get that app to run. Think about how many people are using that app simultaneously. It needs a lot of power. We can't get one machine that's going to be able to do that. So they have thousands, I don't even know the order of magnitude, probably tens of thousands of physical servers to host that one app. So when it gets a request, it's not necessarily going to, there's not like one machine that takes every YouTube request. At that size, I would speculate, I don't know for sure, that there's not even one machine per region. Like you find your closest data center, that's what it gets routed to. I would assume that even in one data center, there are many machines that take requests in like each request is going to go to one of those machines to be routed to a different one. So there are multiple machines just handling the input request. And then those machines will talk to the machines that actually have access to your videos and do the processing and everything. But I would say multiple machines just to handle the web requests coming in and route that traffic. But they have at Google, they have a lot of smart people who worked on it forever. They found out how to build a distributed system where even multiple data centers are running the same app. So you can go youtube.com from anywhere on the planet, and they'll figure it out from there. It's crazy stuff. It's fascinating how those massive apps run. It seems so simple when you go to, like, especially just google.com. I know I'm using Google for a lot of examples, but they're massive, so they have all these problems to solve. Google.com, it's so unassuming when you go to it on your laptop, but it's data centers like this to be able to get that to actually work. Really neat stuff. If you don't think that's neat, you're in the wrong spot. You should switch majors. I don't know. No, don't actually. Stay with us. But I don't know. The more I think about it, the more fascinating it gets. I don't know. All right. So we're plugged in. We got cables running across the entire planet. These cables are plugged into those data centers. We got wireless for like the last tens of feet to be able to connect to those wires. To connect our devices to those wires, and our devices are connected to every other device on the planet through these wires. I keep saying wires, but cables, you know what I mean. So how do we actually use them? Like, how do we actually send a message to the right device that we want to talk to? And that's where the Internet Protocol comes in. So the Internet itself is just a bunch of wires. Internet Protocol helps us turn those wires into the Internet that we know it. So the Internet is a network of networks. If you've ever heard a quick one-line definition of what the Internet is, it's probably the definition you were given. Bless you. It's probably the definition you were given, a network of networks. Well, those networks are your LANs, your ISPs, your tier ones. All those networks all mesh together, and they can all communicate to all of the other networks. So if I want to communicate with someone who's connected to a different ISP, no problem, because both our ISPs are connected to the same network of tier ones who all have the peering agreements, and there is a path from our devices, for our devices to find each other through that network of networks. But how do we actually connect to somebody? Well, IP comes in with the good old IP address. I don't think I really have to introduce IP address, but IP address. The analogy, I won't belabor it. This is a 300 level CSE course, not a high school or middle school course. But so I won't belabor the analogy, but it's basically like your address. It's like your mailing address. On the internet, you have some numbers that define your device, and that's the actual address, how somebody can send you a message. They put your IP address down, send that message out to the internet, and that message is most likely going to make it to the device with that IP address. And every device on the internet has its own IP address for the most part. There are complications with that, but you can address any device on the internet using its IP address. So what we send over the internet are these datagrams or packets. I like the word packets, so that's what I usually use. But we send IP packets over the internet, which have a very small maximum size. You can't send much data over the internet at one time. You can only send a small amount. I forget what that amount is. It changes over time, and it depends on the routers. And I don't know. I think it's on the order of Ks, tens of K. I don't remember. But there's some small limit. You can't just send a gigabyte over the internet in an IP packet. You have to split that into multiple packets and then send that message with multiple packets, which is a huge decision in the early days of the internet that they just knocked out of the park. This idea that you send packets and packets have a small fixed size, is absolutely brilliant. So before the internet, we had phones, like hardwired phones that connected through wires, same way the internet does, for the most part. But it wasn't what we're going to introduce. What we're going to talk about is packet switched. Instead, it was the other one that I'm blanking on the name of. But with the internet, or with the old phone lines, there was a phone operator who would actually plug in your line to another line, and then there was one conductor that you and the person you were talking to were using, and then nobody else could use that conductor. Like, nobody else could use that connection. You used it until you were done, and then that connection was freed up for somebody else to use. When they designed the internet, they said, nah, we want everybody to share connections. We don't want you to plug up a connection, especially if you're sending very little data, then you don't need the bandwidth of that whole conductor. So they said, let's make this a packet-switched protocol. So instead of somebody taking up a whole conductor, a whole connection, you're going to send your packets, and your packets will be mixed in with everybody else's packets and then zipped across the internet. This allows us all to share the entire total bandwidth of the internet without anybody monopolizing that bandwidth. Of course, they can still do things like just flood packets and stuff. But if somebody's sending a whole bunch of packets and I got to send one packet, my packet can be sent right in the middle of that huge connection that's being sent that needs tons of bandwidth. So it's a really fascinating idea, a very elegant solution to that problem that we can all share tremendous amounts of bandwidth because the internet is packet switched. So each packet is going to contain the header and payload. The payload is the stuff that you actually want to send. That's the information you're sending to the other person. This usually includes other protocols. We're going to talk about TCP. We'll briefly mention UDP at some point in the semester. Then HTTP, HTTPS. The payload is going to be the good stuff, the stuff that we actually want to send. And the headers are going to contain a lot of meta information about that packet. Most importantly, source and destination IP address. I need to know where this packet's going, and the routers like to know where that packet came from. Who's receiving that packet is going to want to know who it came from mostly. So IP addresses, IPv4 anyway, looks something like this. 3 numbers ranging from 0 to 255 separated by decimals. It's not actually how they work. They're just 32-bit values, 32 ones and zeros. But as humans, we don't like to read those, so this is how we display them for human consumption. But that's not really, the internet doesn't care about this format. Only we do as humans. So routers are going to read this address and figure out where to send that packet. It's going to send it to what we call its next hop. So it's going to look up, I get this packet, where is the next router in the internet that I'm connected to? I got my routers that I'm connected to. If I'm a router in the internet, I get a packet, I look at its IP address, usually just the first however many bits I need to look at, and then decide which of those routers I'm connected to I'm going to send that to, and then forget it. That's it. And sometimes it only reads the first parts because of prefixes. Certain prefixes belong to certain organizations, so they don't have to read the whole thing. And then that's IPv4, 32 bits. So if we have a 32-bit IP address, we have about 4.3 billion IP addresses. Sounds like a lot. In the early days of the internet where they were making all these decisions, this sounded like a good idea. They said, that's a ton of IP addresses, but that's not enough. Quite a while ago now, we ran out. This isn't enough IP addresses. Think of now, not everybody on the planet has internet access, but a lot of us need multiple IP addresses to go throughout our day. So this number is not enough anymore. So IPv6 came to the rescue, 128-bit addresses, which means we can have this many total IP addresses, which I'm at the risk of sounding naive, I think that's enough. Like, we're never going to need more than that, ever. This number, for some scale, this is much larger than the number of atoms in the known universe. I think we'll be okay. I think we're going to suffice with this one. So they really wanted to future-proof this IPv6. And this is how we send messages through the internet. We need an IP address. As humans, we don't want to think about IP addresses at all. So we have DNS, which is a lookup. We say something like, man, I really do use Google as a lot of my examples. I should change that. We say buffalo.edu. That gets sent to the DNS records. And then we get the IP address and then send a request to the IP address. So we got to talk to the DNS servers first to get the IP address and then send to the IP. That happens in the background. We usually don't have to care that that's happening unless something goes wrong. But we have DNS to help us not remember IP addresses. Did you have a question?
Yeah, like, is there any reason why like most Linux computers start with like 172 as IP and then it's like 192?
Yeah, so that's your local IP address. So if you're connecting to something in your home network to another device on your home network, that's what the IP address is going to be. So that's your IP address according to your router, but that's not your IP address according to the outside world. So your router through the ISP is going to have a different IP address that it communicates to the outside world with.
Even though we implement the Windows and Linux, IP is always different.
Because so like if you go to your device and say, what's my IP, and ask your device what your IP address is that what you mean? So your machine doesn't actually know its public IP address because it can only talk to the router that it's connected to, and the router reports back what the local IP is. So if you want your global IP address, you have to go beyond that router. So when you want your public IP address, you usually go to the internet, go to like what'smyip.com, and then it'll say, well, when I got your IP packet, this is what it said the source IP was, and report that back to us. So that's how we can find our public IP address. Because my laptop doesn't have any awareness of anything outside of UB's network right now. Of course, UB's network gives me a public IP address, so that's a bad example. But if I was at home, it would have no recollection of anything outside of that router's, whatever the router says, unless I force it to go outside of it. Yep.
So when you're making a request to Google.com, is it going to a single computer on one of the server farms?
It will eventually end up at one of their computers, at one of them, yeah. But like if you send multiple requests to Google, you might not always get the same machine. Might not always be the same device. Like there's not one ultimate device where if that one gets unplugged, Google shuts down. But there will be, every request, you will get one of those that will be the one that handles that specific request. And if you want to access websites directly by IP, you can do that as well. Some sites don't allow that. It'll say you have to go through DNS. But this is a way to get around certain restrictions. If you know the IP address of the site you want to go directly by IP. Because like when certain, if certain entities want to block a site, they'll remove it from the DNS records and block it at that level. But if you go directly to the IP, often that'll get through. If you have a use case where that's helpful, that's how you can get around some of those things. If that's useful to you, go for it. If not, whatever. And here's the structure of an IP packet. We don't have to worry about this too much, but most important, source address, destination address. That's where those are going to be. All right. So I mentioned when a router gets your packet, it's going to have its lookup table where it says, where's this packet's next hop? So if I'm R7, I'm going to get a packet, and I need to decide, is this going to R8, R5, R6? I guess those are the three it could get to. I'm getting confused by the diagram I'm using even. But it's going to decide which router it needs to send that packet to, and then it completely forgets about it. Wipes it out of its memory and goes to the next one. These routers are designed for speed. It's got a huge queue of packets it needs to route. It's going to take a packet, send it to its next router, go to the next one, send it to its next router, and rip through them as fast as they can. They're not going to worry about any checks to make sure that that packet arrived where it needs to arrive, which means sometimes your packet's not going to get there. It's not going to get to its destination. So there's lots of things that can happen in the internet for a packet to not arrive, what we call a dropped packet. Sometimes packets just don't get there. The IP is designed to be unreliable because, well, I guess not designed to be unreliable, but it's designed to be fast. And it's designed to be fast at the cost of reliability because all those checks would just slow everything down. So it's up to us to make the internet reliable, and that's where TCP comes in. TCP is going to make sure our packets get there. Or more specifically, if our packet doesn't get there, it's going to detect that and then request a resend and make sure we get that packet sent and make sure it does get there. So TCP, before we just start ripping off packets to another device on the internet, there's going to be a three-way TCP handshake that's going to create a connection. And then through that connection, we're going to agree that, hey, we're going to send packets using the TCP protocol until all the packets are sent. So this connection, first, the client's going to send a message to the server and say, yo, I want to make a TCP connection with you. And it's going to do that by sending a SYN packet, a synchronized packet, with a random value m, a random integer. The server's going to get that value and say, okay, let's do this thing. Let's start the TCP handshake. And it's going to respond with an ACK, an acknowledgement packet of m plus 1, and its own SYN package with a different random value n. Then the client's going to return with an acknowledgement of n plus 1. So this seems kind of silly. We're just going to come up with random numbers and add 1 to them. But what this does is gives a near guarantee for both sides of the connection that they both speak TCP, that they actually have a valid connection, that each side was able to parse the headers, find the relevant information, do some computation to it, and then re-encode it using TCP and send it back to the other side with that plus 1 added to it. So now both sides are sure that this is a valid TCP connection, and they can start communicating over TCP. And then then they can start transmitting data. Usually the third leg of the handshake includes, the start of the conversation. And then each time something's going to be sent over the internet using a TCP connection, we're going to have some fail-safes to make sure that we don't lose data. So for example, if we have that gigabyte file, maybe we're sending a movie over the internet, and we're sending the entire thing, and somewhere in the middle of it, one packet was dropped, one single packet, because of course we have to chop this into many, many packets. One packet's dropped on the receiving end, they reassemble all the packets, video's corrupted, can't play the video, and says, hey, can you send me that whole gigabyte file again? We don't want to do that. So what we do with TCP is split that into separate packets, give each packet a sequence number, communicate how many packets we're expecting, and then once all those packets are received, first of all, they might be out of order, so we couldn't even assemble them without the sequence numbers. But we put them back together, and if we're missing that packet number 500,000, well, they're not, if they're they'd have to be 1 byte each. That's a bad number. But if that middle sequence number is missing, we're going to go back to the server and say, hey, I'm missing packet number 500. And then they can send packet number 500 only. That's the only one that gets resent because we have the rest of the file. We know what we have and what we're missing. And then we can request that resend for that lost packet without requesting a resend for the entire packet or for the entire message. So this is adding some reliability to the internet. TCP adds reliability to IP, so we actually can get the information that we requested or that we're sending. We're going to make sure it gets to its destination. So it's a reliability protocol. We don't have to worry about drop packets. They happen, TCP covers it, and we don't have to think about it. Very nice feature to have. Makes the internet useful, really. Without TCP, the internet would be much, much less useful. If you just are missing random pieces of data, that would suck. All right, so this slide should have been updated too. So TCP sockets in your language of choice, which is Python. You've all chosen Python this semester. In this class, we're going to use a library that's going to do TCP for us. IP is handled at the OS level. We're not going to have to worry about this stuff. This is all background for how the internet works. And then we're going to use those TCP connections in this class. And we're going to start coding at the HTTP level on Friday, which I don't know if I can do the demo today. I might try to fit in the demo today. I probably don't have time. But if you want to know more about TCP IP, I did a very quick overview here. Lots of more information in modern networking concepts. I recommend that course if you want to know more about how the internet works, how these protocols work, all the juicy details about all of this. But in 3.12, we just assume it works. TCP and IP, they work. Your messages are going to get there. They're going to be reassembled. We don't have to worry about sequence numbers or any of that stuff. It's just going to work. I'll save the demo for next time because we do have one more thing we got to do today. It's our first lecture question. Yes. So at Autolab, they submit assignments here. We have Wednesday, August 30. And it's multiple choice. Fill out your choice here. And the question is this. So I'll do the lecture question at the end of each lecture. And once you submit the lecture question, you're free to go. So once I put up the lecture question, that means I'm done. So have a great rest of your day, and I'll see y'all Friday.